And hello, welcome to this video of DWSim. So this was what we did the last video. We are playing around with some heaters and some coolers, of course, and yeah. So we kind of want to move on to the next bit, which is basically heat exchangers. So yeah, that's the next logical step before we move on to a little bit more advanced stuff. I mean, heat exchangers are already pretty complex in themselves, so I mean the number of features that are available in these heat exchangers are pretty extensive. So I'm deleting the recycle stream again just so that we can calculate things a bit faster. Okay, so I'm going to bring out this heat exchanger and it's just going to be called HE01. Okay, so what do we have here? Okay, so we have heat exchangers which will exchange heat between two streams. Okay, so there will be a hot stream and cold stream, obviously, and then you can edit your connections over here. All right, so okay, so the streams need not use the same package, so to speak, thermodynamic package, but let me just illustrate that to you by example. So, okay, so the whole idea of heat exchangers is that we have hot and cold stream interchanging heat. So, for example, okay, after this, after we pass through the cooler, for example, okay, we want to this is some sort of imaginary cooler. I don't know what cooler this is, but yeah. Maybe we want to cool it down some more using some air or whatever thing we want. Maybe even water. Okay, don't know whether we want to mix water with oil, but okay, maybe we will use air cooling. Okay, so we will use air to maybe cool down this thing a little bit further. So this stream is at 43 degrees C, MSTR05, with some amount of heat, which is nice. So I'm going to use this as an inlet stream 1 to the heat exchanger. So that is the first stream. And then this stream is going to have to exit, right? MSTR05. After it goes through the heat exchanger, it must exit. So when it exits, it will be this MSTR06. Okay, so that is, maybe we can call it the hot stream, right? Hot stream. Then of course we want to make a cold stream as well, which is some sort of air stream. So I'm going to create and connect MSTR07 and 08. Okay, so these are streams of air. Maybe we'll just call this air in and air out. Okay, always remember to click enter when you do this DWSim thing. If not, you won't get any good result. Okay, so we have air in and air out, and obviously I want this to be air. So what do I do? Okay, so I will go to simulation settings, and I will definitely want to include air inside here in my compounds. Now go to thermodynamics, and I'm not going to use the cool properties anymore. I will need to include something else. So for this, I will just use well, there's no ideal gas or any equation here, but I can just use Soef-Ridley-Kwong or Peng-Robinson. These are pretty suitable for gases, I suppose, because they are non-ideal fluid models. So I'll just use them. Hopefully they work. I have no guarantee now. Okay, so we can configure this here. Alright, so let me close this. And let's configure the compound amounts in the air in. This one is biphenyl. I don't want biphenyl, I just want air. I'll just accept this. And then of course we'll need to change the thermodynamic package. If not, you'll always this thing will always think it is a therminal, which is not. It is not therminal. Change this to Peng-Robinson. We should be able to get something like this. Okay. So, and let's just pretend for a moment that 130,000 pascals is our pressure in. Now of course we will expect it to have some sort of pressure drop. So our cold fluid in will be, okay, maybe we drop it by 5,000 pascals. Okay, so this is the cold fluid. It drops by 5,000 pascals. Apparently DWSim will just auto calculate this. You will know which is the hot and which the cold stream, so that is nice. So I'm going to save this as, okay, YouTube demo 5 heat exchanger. Okay, because now we actually have a heat exchanger. So this is the basics. Just make sure this thing is in Ping Robinson. Okay, Ping Robinson. Yeah, this thing's in Ping Robinson. And yeah, MSTR06. I was wondering why this air out is cooling down so much. It must be there's the depressurization, so the work is done by the air, even though it is being heated up by this MSTR05. It is still cooling down because of the expansion effect. So maybe expansion we shouldn't give it so much. Let's just put the cold fluid pressure drop to be 1,000 pascals. Or maybe even 0 pascals. If not, it doesn't make sense at all. Okay, soft flow sheet. Yeah. Okay, I don't even understand why what's going on here. AMSTR05 is going in. It's okay. Maybe this looks like a bug for sure, because the air coming out should be heating up because of this. It should not be cooling down. Okay, so well, yes, so there is something wrong with this heat exchanger. Okay, this is the first default calculation mode as of this video. It says calculate outlet temperatures, UA. So what we have here is a global heat transfer coefficient, a fluid in, which is MSTR05. It will pass heat so-called to this air, and it is supposed to increase the temperature of the air for some reason. And let me check this out. Pressure, enthalpy. Oh, right. The thermodynamic properties package is different. As you can see, just now, the thermodynamic properties package here was in cold incompressible fluids. I have to change the properties package to Ping Robinson, and the thermodynamic property package must be the same for air in and air out. If not, you have this funny problem. So we found the bug. Okay, so I guess that solves the mystery of why this temperature has increased. So we need to make sure the thermodynamic properties are exactly the same. Okay, so that is very good. We should have this situation. All right, so let's go through some some of the calculation modes. One is called calculate outlet temperatures using the UA method. Okay, this assumes, of course, that yeah, this assumes that your inlet temperature for both streams are known, and then you just provide the overall heat global heat transfer coefficient, which is U, and the heat exchanger area, which is A. You can also provide some heat loss here to add some realism. Maybe you can put maybe 0.5 kilowatts, which makes sense, right? I mean, there must be some heat loss to the environment because of this heat exchanger. So you can fix that here. It's really up to you. And of course, you can do a counter current or co-current kind of a setup. So this heat exchanger assumes a counter current flow, and then it will just calculate things from there. Okay, this is the calculate outlet temperatures using UA, meaning to say both inlet streams are defined. You define U and you define A, as well as the heat loss. Then the heat exchanged is calculated, and of course your outlet streams are calculated. That's the simplest way, the UA method. You can also calculate outlet temperatures where your I guess from this we are given heat exchange area and heat exchanged. This is what we can play with. Okay, so maybe we can put 8 kilowatts here, and then solve the flow sheet, and then we have an error. Defined heat exchange is higher than the theoretical maximum, so don't do anything. Oh, okay. Maybe we'll do 4 kilowatt instead. Okay, we'll do 4 kilowatts. No, it's 8. Okay, 4 kilowatts. So in theory we cannot put exchange so much heat so much so that the outlet, there's a cross in temperature. You see, there's a temperature cross warning. So we cannot have that happen. Alright. You see that the air in here is 25 degrees C, whereas the stream out here, this is 24.55. So that's going to be a problem. So you cannot actually exchange any amount of heat you want. Anything lower than the theoretical maximum is fine. But then you'll be setting the heat exchanged, and the global heat exchange transfer coefficient will be calculated for you. Now this is assuming you want to design your own heat exchanger. Okay, whereas the UA method, I guess you can assume you know what your U is and what your A is, and you're using that to design your heat exchanger. Okay. And then the other one is that you can specify the cold fluid temperature using a hot fluid outlet temperature, the heat transfer coefficient, and the heat exchange area. You can do the inverse for the hot fluid temperature, where instead you are given two inlet streams. You specify cold fluid outlet temperature, heat exchange transfer coefficient U, and the heat exchange area A. Okay, so this allows you to define what your outlet temperatures are. You are able to control them, at least in theory, when you design this heat exchanger. But if you already have a fixed heat exchanger, then don't use this method. It doesn't really make sense at all. Okay. Then the other one is calculate area, which means everything else except the area. Okay, the whole fluid, hot fluid, and heat transfer coefficient are all calculated for you. Then you calculate the area. So all of these are basically, you know everything else except one unknown. Okay. Now let's go through this. This one's called shell and tube heat exchanger rating. So shell and tube heat exchanger, it really allows you to design shell and tube, like literally. Maybe you have for this you are given a lot of options, like how many shells you want in series, how many shell passes, what's the internal diameter of the shell, what's your fouling factor, baffle spacing, baffle cut. It allows you all this rigorous design of this heat exchanger using shell and tube. And by doing so, all your heat exchanger area, the U will be, of course, given. So this is a shell and tube heat exchanger, very useful. Okay, that's one very common setup. The other one is well, shell and tube fouling factor. So one is that you go for a rating, okay, and this one's a shell and tube with a fouling factor. Okay, yeah, fouling factor is over here. Fouling factor is over here. They even give you a tube layout, which is quite interesting here. Rotated square, a triangle, or whatever those are. Yeah, now I have not actually played a lot with this shell and tube stuff, so I'll probably not do that this video. It probably takes another whole video to explore, so it'll be good to take a look, especially if you already know what your shell and tube heat exchanger looks like. Okay, so this is what comes out of the box. The other one is pinch point, which I cannot exactly remember, but it allows you to define this minimum temperature difference, which I guess in a sense is pinch point. Okay, I haven't done these calculations in a while, so I know what I have heard of this term before, but I'm just not recalling what it is now. But yeah, pinch point, it looks like that you can define the minimum temperature difference across the whole tube, and you kind of use that to calculate everything else. So let's try calculating using a pinch point method. Okay, so you define the minimum temperature difference, for example, here to be 3 Kelvin, your global heat transfer coefficient, and then your heat exchanger area, everything else is calculated for you. Okay. Okay, so this is pinch point. Okay, in my opinion, only the shell and tube is like the most realistic, because in a sense your global heat transfer coefficient is going to be affected by your convective heat transfer coefficients at the hot and cold side. These will in turn vary due to flow rate, and the thing is, you won't exactly get to see you won't exactly know what the you won't exactly get to have the heat transfer coefficient vary with flow rate, except in this shell and tube heat exchanger sort of a setup. Okay? Only that will calculate it for you. Pinch point also, you have to define this global heat transfer coefficient yourself. Okay, let's see. Heat transfer efficiency. Okay, this allows you to specify heat transfer efficiency given a global heat transfer coefficient. Again, not so good, or rather not good if you have a fixed heat exchanger. You pretend you have a fixed heat exchanger, and then based on the flow rates, you will then calculate the heat exchange or the Nusselt number and everything like that. Okay. The other one is specify molar vapor fraction, outlet molar vapor fraction for hot and cold stream. This is something I'm not touching now because it involves phase change and mixtures for that matter, so this is not something I'm doing. I'd say among all of these, the most realistic ones are of course the shell and tube. Okay, but the most simple ones are of course this UA method, where you can just define your U approximately, and you define your area, and then you have your heat exchanged. Okay, and based on this, you should not ever have a temperature cross situation, because you're not defining any sort of temperatures, right? You're not you're not defining any of these temperatures. So just so you know, let's recap. If you want two different types of fluids, you need to select you need to edit a thermal properties package under here, and you have to make sure at both the inlet and outlet the properties package are the same. So let's say for the air stream, I need to make sure the inlet and outlet are both Ping-Robinson equation. Otherwise, you will see that the thing becomes buggy. It will give you results that don't make sense. Okay, we also went through all the above heat exchanger sort of calculation modes, and we found that the shell and tube method is by far the most so-called close to most realistic. Okay, and now if we put this back to recycle, we should be able to use this recycle stream thing. Okay, so anyway, let's take a look at shell and tube again. Yes. The other thing I forgot to mention is that pressure drops are normally also very much dependent on Reynolds numbers. Okay, and you should not manually like define them. unless you already know what your flow rates are and you want to fix your flow rates. But for a realistic scenario, you will then need something else to calculate the pressure drop across maybe this shell and tube heat exchanger. For that, I strongly suggest you use this shell and tube exchanger rating or fouling factor method. Go and play around with them, and then you will see that your pressure drops for hot and cold fluid are appropriately calculated in a more realistic manner. Okay, so that you can play around with them eventually. Okay, so now let's connect up the recycle stream. Everything should still work out nicely because remember we had our fixed points. Once we have our fixed points, it should be relatively easy to iterate your recycle stream. So we'll connect this to terminal stream inlet. So there's the air, there's the cooler here, and then we have a heat exchanger, which is basically air cooling. Yeah. So just for what you can actually pretend there's a centrifugal pump actually blowing hot air or cold air into this heat exchanger, and it basically works like a fan cooler, right? It is that's what you can think of it as. Of course, in a sense, for exchangers here, you actually have this air cooler thing here, which is, I guess, the even more realistic than this shell and tube if you want to use air cooling. But this is a DWSim Pro thing. Okay, it is not available here. You have to actually pay for it. So it's not free and open source, unfortunately. If you want to design something more custom, you might want to go to user models and design your own Python script, which as of this video, I have not tried yet. But anyway, this is what is available out of the box. For a lot of our applications, it is enough. So let's play with the recycle stream. And as you can see, this thing solves very quickly. And within 0.3 seconds, the whole recycle stream converges. Why? Because we have a fixed point here. The pressure fixed point is here. Okay, the temperature fixed point is here based on this cooler. And of course, the flow rates of terminal is fixed throughout the loop. So the thing will converge very quickly. Yeah, if you don't fix those points down, it may not converge quickly or not converge at all.